All right, so let's just continue with Gibbs energy. So this is the very important equation over here, which connects change of Gibbs free energy with change of enthalpy and change of entropy. And there is a T over here. So it's delta G is delta H minus T delta S. And H, S, and G are state functions. So if we look at this picture here, so see, this is the Gibbs free energy here. This is Gibbs free energy. This is time of the process, for example. And you can see at the beginning, which says over here reactants, right? So the energy of reactants is higher than the energy of products. So if we have situation like that, that initial energy of the reagent is higher than the energy of the product, then this system might take spontaneously. Why? Because this delta G is going to be less than 0. So you can see, right? So if you subtract this part, initial part from the final part, this delta G will be minus sign, right? So less than 0. This is why the process like this, it's spontaneous. But opposite, when you have at the beginning low energy, but the energy of the product is high, then this process cannot take spontaneously, because see the bump, how high is this one and how low is this one? It's kind of the same as climb on the mountain, you know, which one is easier? So this is easier, right, than this one. So, and also at the same time, the product might not be stable, it can go back. So because of that, the first system is called exergonic, the other one called endergonic. So you might have a situation like this. So when the initial energy and the final energy are the same, so this kind of system is at equilibrium. Basically, no change in there, right? So this is going to be at equilibrium. But this equation is very important. So let's just discuss what can it tell us. If you look at this table, so we have this equation here. Delta G is delta H minus T delta S. So this table is very convenient to understand the system is going to be spontaneous or non-spontaneous, or what is the condition to make it spontaneous, and so on. For example, if delta H is positive, right, and delta S is also positive, then it says over here that delta G is going to be a particular amount, right? And what's going to happen in this situation? It says that reaction proceeds spontaneously at high temperatures.
It's
Okay?
proceed spontaneously and high temperature.
Right. And at low temperatures, reaction is...
Reaction.
Okay, so let me finish here.
Direction.
Yeah, let me finish. At low temperatures, reaction is spontaneous in the reverse direction. So what does it mean? Now I'll explain. Say you have delta G equals delta H minus delta T delta S, right? So it's written over here, but let's rewrite. Now let's look at this one. So this one is always positive, right? It says it's always positive, and this is always positive. So what do we need to make delta G to make the process spontaneous? So we need to have delta G less than 0. If we have delta G less than 0, then the process is going to be spontaneous. So when delta G can be less than 0, it will be only when this T is very high. Okay, in other words, T delta S is more than delta H, right? If it is the case, then delta G is going to be less than 0. So when it can happen? When T is high.
Doctor, the temperature will be 0 Kelvin.
No, temperature needs to be in Kelvin, yes, but it needs to be high. Okay, I don't know how high, it depends on the process, but it needs to be high because this term needs to be more than delta H. And we know that delta S is plus, delta H is plus, so only thing we can change here temperature to make this part more than this part. Okay, is that clear?
Yes, doctor.
Okay, now let's go to the next case, plus and minus. So delta H is plus, delta S is minus. So what does it mean? Let's just again look at the equation. So delta G.
Doctor, mean delta H big more than delta S?
Yeah, so it means that delta H is positive. Delta H is positive. So it means that it's difficult to compare these two because these two are different parameters. So this delta H is enthalpy and delta S is entropy, but in terms of numbers, yeah, we can compare in terms of numbers, right? But let's just look at equation first. So since this is plus, we just write, so delta H is plus, we just write delta H, right? Then after this, it goes like minus T, but now with delta S, we have minus, right? So it means that we need to multiply this T on minus delta S, right? Which is the same as delta H plus T delta S. Do you guys agree?
I don't understand.
Okay, so what you don't understand? This is simple mathematics. You need to, so you just need to convert this one. If you have minus here, so do you know what does
Oh, okay.
Okay, so
I get it.
did you get it? Okay.
Yeah.
So now
Thank you.
this is plus, right? So it converted to plus, right? So now look at this equation. So whatever you do with T or whatever you do, delta G is going to be always what? How do you think? More than 0 or less than 0?
More than 0.
Of course, it's going to be always more than 0. There's no way to make it less than 0. No way at all. Whatever you
Doctor,
do, yeah.
in every situation, he depend the T delta S.
In this situation, nothing depends on T actually, because whatever you do with T, you will never change the situation that delta G is more than 0. Even if you make it 0, if you make T 0, then it just equals to delta H with each positive. So again, it's going to be more than 0. And you cannot make T minus because it's in Kelvin, okay? It's not in Celsius, it's in Kelvin. So you cannot make minus Kelvin, doesn't exist. Okay. So, and then what's the situation? So it says delta G is always positive. So what does it mean in terms of like spontaneity? Is it spontaneous or non-spontaneous?
Spontaneous.
It's
Because-
spontaneous.
If delta G is more than 0, is it spontaneous process or not spontaneous process?
Spontaneous process
It's
because
spontaneous process.
the G always positive.
Okay, so when delta G is always positive, the process will be non-spontaneous, okay? It will be it's not gonna be happen itself. So that's the situation when delta G is positive. When it's more than 0, it's not gonna happen itself. So it means that you need to spend some energy all the time in order to make process happen. Okay, you need to remember this one, that delta G positive means that process is non-spontaneous. It says over here, reaction is spontaneous in the reverse direction. Okay, so this process is non-spontaneous, but this might be spontaneous. So you cannot make ozone from oxygen easily, but you can decompose ozone to oxygen easily. Okay, so this is what does it mean. So if, for example, now let's just go to next one, next case. So delta H is minus. Now let's just change everything. So delta H is minus and delta S is plus. Right? Let's just write it here. So it means that we have delta G equals, delta G equals minus delta H, right?
Right.
Then minus
delta
T,
TS.
T delta
T
S.
delta S.
Right. So in this case, whatever you do, you will get delta G always what?
Minus.
Exactly, minus,
Negative.
which means that it's less than 0.
Yeah.
Always. So it means that delta G is always negative, which means that reaction proceeds spontaneously at all temperatures. Okay? Any
Yes.
temperature you take, it's going to be spontaneous. And this is the example. For example, this is hydrogen peroxide. And if you just leave hydrogen peroxide on air, it will decompose. It will decompose in water and oxygen. Okay, so this process goes spontaneously. You don't need to do anything with that. You just put hydrogen peroxide, open bottle on the bench, it will decompose. Do you guys get the point?
Yes, doctor.
And let's just consider the last case. I'll delete this one.
Should we memorize the reactions example?
Yeah, these are reaction examples, yeah. And the last one is then when delta H is minus and delta S is minus, both of them minus. Let's see what's gonna happen. So we have delta G, which equals to minus delta H. And because this is minus here, so we'll have
And
plus.
minus.
Yeah, so it's the same as plus delta S.
Plus.
Now, it says over here that the reaction proceeds spontaneously at low temperatures. It means that this part must be smaller than this in terms of like numbers. Okay, so if the temperature is very high, then this is gonna be more than delta H, and then delta G will be positive. But if temperature is low, if it is very low, the term delta S, T delta S is small, right? Because the temperature is very low. So if it is small, it means that delta minus delta H plus small, very small delta S is going to be again minus, right? For example, if delta H is minus 5 and T delta S is 3, then it's going to be minus 2, which means that it's negative all the time. Okay, and delta G is going to be less than 0 at low temperatures, which means that reaction proceeds spontaneously at low temperatures. All right. So this is it clear, everything, like all these 4 cases?
Yes, doctor.
Yeah, it's very convenient to evaluate at the beginning if the process will go spontaneously or non-spontaneously. It's very convenient in that sense. So, okay, now let's just look at the real example. What we can do with these calculations and, you know, delta G, delta S, delta H. So how can we use all this information? For example, if we have the amount of delta H, right? This is amount of delta H. This is
Kelvin.
temperature. This is temperature kelvins. This is entropy, right? This
Yeah.
is conversion factor. Don't forget that entropy is joule per Kelvin, but enthalpy is kilojoule per mole. Yeah, so you need to convert joule to kilojoule or opposite, kilojoule to joule to make like normal calculations. So this is just conversion factor, and then you can calculate delta G. It's 130 kilojoule per mole. So it means that this process is not gonna be spontaneous, right? Because delta G is more than 0, so the process will not be spontaneous. Now let's just see when the process, at which temperature the process can be, for example, spontaneous, right? So it means that let's try to find out the temperature. So basically by changing the temperature, we can change the delta G. It means that we can change the process going spontaneous or non-spontaneous. So let's just see how to find out which temperature makes this process spontaneous. Okay, so what we can do is that we can just make equilibrium conditions. Say delta G is 0, then we have this equation over here, right? And then let's just put parameters, all parameters in here. So we have 177 kilojoule per mole. This is conversion factor. This is entropy, right? And then we can find temperature. So from here, we can find temperature, right? Because T is delta H divided by delta S, right? According to this equation. It's just the same thing, right? Then let's just put instead of H, delta S, what we have. So 177.8, then 160.5. And we found the temperature is this. Okay, so we found that if we have temperature like 835 Celsius, this is the same as 1108 kelvins, right? So if we have the temperature like this, we will have delta G 0, right? Agree? So in order to make delta G less than 0, then we need to increase temperature. So it means that we need to put temperature higher than this. So this is what does it say? At temperature higher than this, delta G becomes negative, which means that, say, if you put temperature like this one, for example, which is more than 1108, right? So this is more than this over here, right? So if you put temperature like this or even higher, then all the time delta G will be minus. So it means that at this temperature, so if you want to make some kind of process, say, I don't know, melting of the iron or anything like this, or quartz. So it means that you need to provide temperature higher than this. And then if you know the standard enthalpy of formation, standard entropy of this, for example, I don't know, system, so then you can calculate the temperature, and if you put temperature higher than this, you will make spontaneous process. So, okay, so we're talking about these equations like delta G, delta H, delta S, but what does it mean in reality? For example, why do we need to understand energy changes and thermal changes like in the life, right? And since we are talking about medicine, so why do we need, for example, this one to do for the medicine, right? The point is that I explained at the very beginning, like last week, that if we do not have normal temperature in the organism, then the processes will take place in a different rate. Either they will be very accelerated and going in a very high rate, so we'll talk about kinetics next, or they will slow down. They will slow down, and the process is, when it's slowing down, it might change everything in the functioning of organisms, right? And for example, this kind of thing is used also positively, not only negatively. For example, when there is an open heart surgery, so heart does not need to work hard very much, right? So the beating of the heart needs to be decreased because during the surgery. So this is like might be technically kind of requirement for the surgery, right? And how to decrease it? So what is happening that the temperature might be provided like low temperature and cooling down the organism, okay, in order to make heart beating low. But at the same time, since heart needs the organism needs to have circulation of blood, so it's like externally is provided, okay, externally. But naturally, heart starts to beat slow because of low temperature, and then the heart surgery can be made. So this is very important, actually. This kind of energy changes and heat change is very important. I'll not stop here. It's also a very important equation, but I will not stop here. This is just a relationship between Gibbs free energy and the rate constant of reaction. So we'll not stop here. I just want you to look at thermodynamics in living systems just as an example. So it's also quite well studied and understood. For example, the conversion of glucose, burning, basically the burning of glucose gives away energy in terms of heat, right? So it means that it loses the energy. So this energy goes somewhere, right? So this energy can be stored, released energy during burning of glucose. This released energy can be stored in the organism, right? And then used for some other processes. For example, to convert ADP to ATP. So this is adeno diphosphate conversion to adeno 3-phosphate. Okay, this process is endothermic because it's opposite. It requires energy. It doesn't give away energy. It requires energy to be spent in order to make this process happen. So how can we take this energy? Where we should take this energy from to spend it for transformation of ADP to ATP? We can take it from here. All right. So this is like thermodynamics in living system, just an example, but the whole living system depends on the thermodynamics of the processes. Okay. Any other questions here? This is the last slide. Do we have questions for this part of our class?
Doctor,
Yeah.
and the last thing, glucose spontaneous.
The burning of glucose
Well,
on those
yeah.
conditions which we have in organism, yes, it can go spontaneously. So the temperature is enough, so we have oxygen. If we are breathing and we have oxygen, then it can be burning. Yeah.
ADP unspontaneous. Yes, Doctor.
But yes,
ADP.
but conversion of ADP to ATP is not spontaneous. So you need to provide energy.
Not spontaneous.
Yes.
Doctor,
But
Because
opposite,
delta G is positive.
and
but
Doctor, and the
opposite,
next
opposite,
lecture
opposite process can be spontaneous from ATP to ADP. So opposite process, if you reverse this process, it can be spontaneous.
spontaneous.
Right.
And in the reverse. Yes. Doctor, in the next lecture we must calculate the AG and
For the exam, we will have these kind of things for the exam. So we will have one case when you need to calculate, say, something, temperature on which, say, the process will be spontaneous, or delta G will be higher or lower. So this kind of thing, yeah, on exam you will need to calculate. But we will practice a little more about this one to understand, so that it will not be like something difficult. It will be very similar what we discussed here. Okay. Very similar. Also, I want you to understand this also. It is very helpful. I want you to understand why we have different delta G's when we have different delta H, delta S. So everything comes from this equation. If you understand this equation, then everything is very simple. This is not complicated equation. Any other questions about this part?
No, thank you.
All right, so look, I want to start another part, so which is we are a little bit behind for some reason. So I want to start another part, which is kinetics. So because I want you to understand that
Doctor,
this is-
can
yeah.
you start it in the last week and the next week?
Why we have time, so we have 2 classes, right? So we need to start now. Why we should start next week? I don't
Yes.
know, because we have time.
Yes, doctor, because
No.
yeah, but we are tired from.
I know you
studying
are tired,
to
but
the
you are tired, but you know we need to stand it. So
yes,
okay.
okay.
By the
It's
way,
okay.
you're supposed to have 3 hours per week, because the 1 hour is the lecture, just you need to listen, just recording, but 2 hours is practical. Yeah, it's not easy because we do not have break, right? So we do it without break, but you know, it's just only 40 minutes, so we should be strong. Okay, so let's just start with kinetics, and let me just open and share it with you. Okay. Do you guys see the slides now?
No, doctor.
All right, so no or yes?
No, yes.
Okay, so what I want to explain, so before last 2 classes, we talked about thermodynamics, which tells us if the process can go or it cannot go. So it tells us if it is spontaneous or non-spontaneous. So this is what we can find out from thermodynamics. But for example, if the process goes on, right? So it started and it continues. After this, we are interested how fast is the process, because it's also very important if it is slow or if it is fast. So all these things is studied by kinetics, chemical kinetics. Okay, simply it just shows us, I'm sorry, so it just shows us how quickly the concentration of the chemicals can be changed per time. So basically it shows us rate of reaction, rate of conversion of chemicals. All right, so it's the same as just the rate. So for example, when you are driving the car, so what is the rate of your of driving? So it's change of distance per what?
Of acceleration, doctor.
No,
Maybe.
say you already reached acceleration and then now you are just driving, but with constant rate. So what's going to be the rate? It's change of distance per what?
For your path.
Per time.
Per time, of course, it's change of distance per time. That's the rate of movement, right? Of the car or whatever, doesn't matter, or
Yes.
person. So it's change of distance per time. So the same thing, very similar one, is in chemical reaction. It's change of concentration per time. When we're talking about the rate of reaction, it's always like, you know, per time. So anything in terms of rate, it's per time, right? And how can we express it? It's just very simply written over here. So it's Say if we have A, which is transforms to B, it means that we have delta A over delta T. So this is delta A is concentration of delta A to delta T. Is the same. So this rate and this rate will be the same, exactly the same. So what is difference? It just shows the formation of B, okay, per time. So this is consumption of A per time because this is initial one, and this is product. And this is just the formation of delta B per time. So just to understand it's better. So look, this is the concentration here. This is the time. And we have two lines over here, two curves. One is product, which is B, and the other one is A. At the beginning, this is 0 time. So say it's very general scheme, but say this is in seconds, right? Second. At 0 second, we had B, which is product 0, right? So that's the 0 concentration here. But we had a lot of A, right? So we had at the very beginning a lot of A, nothing about B. Then we just continued the process, say at this point, so we produced B, but we consumed A. Why? Because now it's getting small and this getting big, right? So at some point again, so we have even less A, but we have a lot of B, right? So this is B, this is A. So for time, we are producing B, but decreasing A. And but at some point, B goes to plateau. See, it doesn't increase anymore, right? It just goes to the straight like this one. Why? Because we do not have any more A. So we just used up all the A we had. So this is why B doesn't change anymore, right? So do you guys follow this?
Yeah, of course.
Okay. So now let's just see a little bit different situation. Say we need to convert 2 A's in order to produce 1 B. So it means that we need to have 2 moles of A disappear for each mole of B that forms B, right? So the rate at which B forms is 1/2 of the rate of which A disappears, because 2 A's disappears, 1 A is formed. So the basically disappearing of A is quicker than formation of B. So how can we express this one? It's also very simple. So we have rate, change of concentration of A over 2 times delta T. So this 2 is here. But the rate of formation of B is just the same as change of B over delta T, right? Now, say we have equation like this. We have A, small a, B, C, D, right? We have these coefficients A, B, C, D. So this is a chemicals. A, B, C, D are chemicals. Capital A, B, C, D are chemicals. Small a, small b, small c, small d are coefficients. How to write the rate expression? So we can write like this way. So disappearing of A over times A delta T, and we have minus because it's disappearing, right? So this is why we have minus over here, equals to disappearing of B, the rate of disappearing of B, right? Over B times T, and it equals to appearing of delta C, right? So because now we have product C, so now there's no minus anymore. So C appears, and C it's over C times delta T, and the same about D delta T over D times delta T. Now let's just look at this one and try to write the expression, rate expression for this equation, okay? So we have 4 moles of ammonia reacting with 5 moles of oxygen. We make 4 moles of nitric oxide plus 6 moles of water. Can you think about the rate expression for this equation?
Doctor, I think minus rate at the first. We write minus 1 divide 4 and H3.
Okay, so we should not forget that this is the delta NH3,
Delta
NH3, and you need to make this kind of sign because this is concentration of NH3. So-
Divide time, but
Delta
Doctor,
time.
we don't know the time.
Yeah,
How
we don't know the
can-
time, but we know that this is time, delta T.
Delta T
Then,
equal minus 1 divide 5 delta OH2 equal 1 divide 4 and equal 1 divide 4 NO.
yeah, delta O and O. What
delta
is here?
NO
What is here?
Time.
Delta T, right?
Delta time, yes, of course. Equal
And yeah,
1 divide 6 delta H2O
right.
divide delta time.
Yeah, so it's not very difficult, right? So you can just write down the
Yeah.
equation like this. So why it's convenient? So why it's convenient? For example, if you have a reaction like this one, right over here, and you know that rate of reaction of molecule of oxygen is this one. So 0.037 moles per liter per second. So and then it asks what's going to be the rate of N2O5 being formed. So it's very easy to find out. So this is the rate of change of oxygen, right? So if we write rate is minus delta O2, which is here, over delta T, it equals to this one, formation of this one, right? They're the same thing. We don't care about this one by the moment. So then you can write something like this, right? Then what you can do is that you can just plug the number, which is this one.
Doctor, will be the same. Just
Yeah,
we
it will be
divide
the same. Yeah, so
one divide 2.
yeah, so then you just plug this number over here and then solve this equation. I have less than 1 minute, but let's just finish here everything. The same thing about NO2. I mean, the same thing you'll do exactly for NO2 over here. Then you just plug oxygen, the change of concentration of oxygen, and you will find what is the rate of change of NO2. So it's very convenient, very simple approach. Do you guys understand or not?
Yes.
Yeah,
Yeah.
of course. Thank you, Doctor.
Doctor,
Doctor,
Yeah.
will you please upload the last file and Moodle?
Yes, I'll upload this last file also.
Thank you.
Doctor, before we end, when will we start the lab?
Well, I'm thinking next week.
Next week in the particular time. Yes, Doctor.
Yeah, I'll let you know about particular time because we need to split the lab.
Yeah.